Okay, we're going to look at our third video, Implicit Differentiation 3, where we're looking at equations of tangents and equations of normals to a curve at a point where we require the use of implicit differentiation. So please make sure you've watched the first two videos before you watch this. Now, what we also need to remember is not just have our implicit differentiation intact, we need to remember a few underlying concepts from our previous study of certain mathematical methods. And as we know, that the derivative dy dx is a story about the gradient. Okay, so we can, basically call it a gradient function, and you would have done that in the past. And it's a function which describes the gradients at various points. Now, a tangent is a straight line which touches a function at a given point, and we can look at finding a tangent if we know the gradient at a point. And if we know the gradient, we can find the tangent's gradient because it's one and the same, and you need to have a known point in order to find the gradient of the tangent. Now, with that together, you can come up with the equation of the tangent at a point, which is the equation of a straight line using y equals mx plus c, or in standard form or implicit form. Now, once we've got that, we can find, if we need to, the normal, which is perpendicular to the tangent, which means that the gradient of the normal is the negative reciprocal of the gradient of the tangent. In other words, if they multiply together, they equal -1, perpendicularity. Looking at an example now, find the equation of the tangent and the equation of the normal at the point 1, -2 of the following function given below. So we start by applying our implicit differentiation, noticing that there is an application of the product rule there, and we carefully go about that, and we'll have 3x squared, and putting in the product rule, so we have 3x times dy dx plus 3y, there's the product rule part there, and we have 3y squared dy dx. The rest of it comes out as 0. The constants end 0. Okay, moving forward, then we do some rearrangements there, so we can isolate dy dx, and on the left we can take a factor of dy dx outside, leaving 3x plus 3y squared inside. It's a squared. Oh, bit of a gap there. Apologies for the gap. Mind the gap. Alright, so try and be a bit more considerate of my use of space from here on. If you can forgive me for that error in my formatting. And I'm just dividing through by 3x plus 3y squared. So dividing top and bottom by 3, we get -x squared minus y over x plus y squared. Now at point of interest is the point 1, try again, sorry. Now at the point 1, -2, the point of interest, we have the derivative, or indeed the gradient of the tangent, will equal the substitution of x equals 1 and y equals -2 into the equation. Remember, minusing -2 is +2 on the numerator there. We have 1 plus 4, and that boils down to 1/5. So the gradient of the tangent is 1/5. So for the equation of the tangent, one way of going about it is consider y equals mx plus c, and we have a value for y, we have a value for m, that's 1/5 from just above there. Alright, and we have a value for x, which is 1. We need to solve for c. You can use the point gradient form too. Just down to personal preference. You just need a point and a gradient, so you can use that as well. I'm just using straight substitution. And we have -2 equals 1/5 plus c. So we have -2 and 1/5 is c, or -11 on 5, more usefully. Okay, so our equation is y equals 1/5 x minus 11 on 5. Now it's probably proper to put this in standard form or implicit form, because hey, this is what we were given, we should give it back in implicit form. Okay, so while that's correct, we need to multiply through left and right by 5, and we have x minus 11. So implicit form will be -x plus 5y plus 11 equals 0, and multiply all the terms by -1 to make your leading term x a positive. So we have x minus 5y minus 11 equals 0 as the equation to the tangent. Now, because it's perpendicular, the normal has inverse reciprocal relationship with the gradient of the tangent. So the gradient of the normal will be -5 because the gradient of the tangent was 1/5. Okay, and we just go through and use the same strategy using y equals mx plus c for the normal. Now the point is common to both the tangent and the normal, the point of contact. Okay, so we keep using at the point 1, -2. Again, we use that. Alright, and we sub that in. -2 equals -5 times 1 plus c. So we add 5 to both sides. C equals 3. And then we can update our equation. Y equals -5x plus 3. And in implicit form, the equation of the normal is 5x plus y minus 3 equals 0. So that's the equation to the normal. And if you like, you can verify with technology. So we have the equation of interest there in red, and we can see that firstly the equation of the tangent, and it matches and it has a point of contact of 1, -2. It's just being a bit problematic there. Anyway, it's pretty much shown there. And look, that's at right angles. There you go. It needed all three there. So 1, -2. And that shows you the original curve in red, the equation and the line of the tangent. And at the same point, 1, -2, we have the equation and the line of the normal, all at 1, -2.